Okay, let's have a look at diffraction through a single slit. Now, we've done diffraction through double slits, young slits, and we've looked at diffraction grating. Well, if you haven't, you can look at the video. But this is diffraction through a single slit, and we can use Huygens' principle again, that in the slit you've got a whole bunch of points which act as sources for a wave. And what we're going to ask ourselves is, and we're going to try and work out mathematically what happens with this. Now, we've got the same setup we had with two slits, and we can split this slit into 4 zones. So each of these would be d over 4. If I take 2 points in the slit that are half d apart, and we have them hit the screen over here, then as before, if we assume that the screen is a long way away and that the lines are for all intents and purposes parallel, then what we can say is that d over 2 times the sine of theta, right, d over 2, half the slit length, times the sine of theta will be the path difference for the waves. So to get a minimum over here, we will need that to equal half a wavelength over 2. So we can cancel those and say that for destructive interference through a single slit, d sine theta will equal wavelength. Now remember, for our other one which we did with the diffraction grating, d sine theta equals n wavelengths, gave you constructive interference. So with this situation we get destructive interference. Now I just took 2 points half a wavelength apart, but I could do that for an infinite number of pairs of points in that gap, and it would always hold true. So this does hold true. So I could take a pair here to here, or here to here. You see what I'm saying? Now if we look at that pattern, when you actually draw the pattern, let me get another bit of paper, you'll see a pattern like this. So what pattern am I talking about? I'm talking about the pattern on the screen. What will you actually get? So actually on the screen we've got this midline here, and you'll see this pattern sometimes. I'll just turn an edge on so that I can draw it. You'll see this pattern, and you'll get this central maximum, and then you're going to get your first minimum out to the side. Then you'll get so that's your first minimum at that point. That's your central maximum. So when we look at this here, what we can say is that relationship that we just got, and that is that sine theta is going to equal wavelength over d. Okay, we just said that d sine theta equals wavelength for a minimum. So this minimum here or this minimum here, we can say happens at wavelength over d, wavelength over d. That's the first minimum, and that's diffraction through a single slit.